Okay, we're still live streaming. We've got that YouTube as well, and a final presentation from Steve Bress. Thank you, Steve. Okay, good luck.
The most important thing, the clicker. I'm Steve Bress with, sometimes it says Entropy Engineering, sometimes Celestrial Circuits. Today we'll go with Celestrial Circuits. Entropy Engineering is a company I've had for a very, very long time, done everything from data acquisition to space stuff, security stuff. Usually what happens is we get something interesting enough, we'll spin it off to be its own company. And the space stuff, especially with NanoRacks, has gotten interesting enough to pretty much set up a separate company just to specialize on the space-related parts. Now, Mike was showing the cube earlier and our controller board. And basically, it's a small data acquisition system. It collects data, and it's small. In the old days, this was what a small data acquisition system looked like. Those fit into nice 19-inch racks like you'd find in any kind of industrial location. And I built the controller boards for those things. They have nice big tape drives, the predecessor of SCSI. Their claim to fame around these parts is they were used before the first shuttle flew. Sounds loud here. They were used before the first shuttle flew to help categorize the stresses on the shuttle bay doors to make sure that they were actually working right. So, my history with space stuff does go back a little bit. Similarly, we built things a little differently in those days. That board is about 1 foot long. The back of it is all wires. Most people get scared when they see that. These days, it's a little simpler. The NanoRacks control module that we build is about 3.6 is the new size. You don't see too many random wires sitting on it, and the power consumption is a little bit less. But more importantly, it's small enough it can actually fly inside a cube instead of having to grind up something bigger to get the debris into a cube. So, welcome to the presentation. Our little cube robot. As we like to say around here, for a lot of space experiments, you start all the way at the beginning and say, I want to do an experiment. And, well, I'm going to have to build a computer, I'm going to have to build this. Well, in chemistry, you wouldn't do that. You go out and buy a Bunsen burner. And you buy the glassware, you buy everything you need, and then you actually do your experiment. Well, for a lot of space experiments up till now, it's really been the old way that you just had to do everything. You built your own computers, you built your enclosures, you just spend all your time recreating the infrastructure that hopefully hundreds of people have done before you. So we're trying to really standardize the interfaces. There was talk of open source and open implementation. Well, we're trying to make it so simple that you buy a computer, you hook it up, you do what you want. Now, so that's the good part. Now, the downside to that is the doing what you want part comes down to you. That I can build you a nice general purpose computer, you still have to tell it what you want it to do for you. And I can't design your experiment for you. There's another piece of flight hardware we have. It's on the plate reader, I believe, up on station right now just to help control the cooling. So we have actually flown some stuff. As part of what Celestrial Circuits does, we're not only looking at the NanoRacks for flights, but we're also looking at every other type of flight experience that would lead up to an orbital. So from tower drops, suborbitals, and all that. And we're trying to create the hardware to be able to do it, as well as curriculum to be able to teach it. Because the idea is, if you had a school doing a really interesting experiment, there's no reason that 1,000 other schools couldn't have ground truth. And their ground versions using virtually the same equipment, and that just makes it interesting enough to be able to bring in students who otherwise wouldn't have a connection to it. You can't necessarily fly 1,000 experiments tomorrow, but you can certainly have 1,000 people doing their version of ground truth, whether that's just watching a plant grow on the ground to compare to what comes back later, or whatever the experiment calls for. So we're working on a curriculum that matches all the state-mandated details, so it could be used and could become part of the educational world. Now, your experiment is basically your imagination. we're, we're giving you a 4-inch cube, and you have to put things in it, and hopefully make it interesting enough to be selected to fly. What that is, nobody here today is telling you what to do. You can, whatever you can imagine can fit in. There's going to be some constraints due to NASA and due to physics, and we'll go over some of those. And I've done enough of these talks that a lot of the teachers get very upset with physics. And it just makes them very sad that they can't do the things physically in a 4-inch cube they would like, but I can't solve that one for them. But what we can do is provide the tools to make it easier to do. There we go. We can provide the tools to make it easier. The real-world restrictions, some of the stuff that Mike has talked about earlier, you have power limitations, you have size limitations. You're actually not in a vacuum. So if it was important to have a vacuum, well, you don't have it. And NanoLab is a specific format. It's a specific size. It has specific power. It has data connectivity. And everything about it matches what it needs to fit into the rack on ISS. So it has some restrictions. There's always restrictions. However, working through them, you can still do quite a number of different experiments and do some very exciting things. For the NanoLab, the size is 100 by 100 by 100 millimeters, or a 4-inch cube, depending on how you like to talk about size. Now here's where I have a discrepancy with Mike. He told me in the past it was 5 volts at 500 milliamps, like every other USB device, but so somewhere between 2 and 2.5 watts. We'll argue it out later, but if you can run on 400 milliamps, you can certainly run on 500 milliamps, which basically is a good plan anyway. If you can build a margin into your experiment, you're going to end up being a lot happier. If you're told the budget is 500 milliamps and you design everything to fit exactly 500 milliamps, well, when you decide you need to run the processor 10% faster and you go over budget, you could be sad. Now it's the same power available to standard USB 2. The reason we say USB 2 and not 3 is 3 bumps standard to up to an amp and in some cases more. So USB 2 is a safer discussion. The communication is USB 2 high speed, but there's a catch. It has to be a USB device that follows mass storage specification, which means to most people who don't care about mass storage specifications, it has to look like a thumb drive. And part of the reason for that is when an astronaut floats by, there's no drivers that suddenly have to be installed in their computer to do a data dump. They just drag and drop the files. Or if you're putting data onto the NanoLab, they drag and drop a file onto the memory that looks like the drive. Now, Mike will correct me if I'm wrong on any of this. So getting a small device to pretend to be a thumb drive seems easy. It has enough intricacies which most people don't want to do or don't want to have to know anything about it, which is why we make a control module that takes care of all those details for you. Space itself has some of the constraints. You have safety considerations. Everybody's been talking about the reams of paperwork. Like Mike's been saying, he'll take care of all the paperwork. If you try to fly too much plutonium, he's not going to be able to fly it for you. You have a launch vehicle that's not necessarily in this country. Preferably it will be, but it's not necessarily. Every launch vehicle has its own restrictions, and every country has its own rules about what is going to be allowed to fly. So if you're flying seeds and water, I doubt you'll have much of a problem as long as your containment is good. If you want to fly something more ambitious, okay? It's okay, I'll try not to say anything interesting while you're gone. Okay. Anyway, so the launch vehicle's half of it, and that was a big deal when the shuttle was flying because they were all NASA people, but they had completely different rules about flying on the shuttle and flying on ISS. As if you would think if it could fly on the shuttle and that was the main way to get to ISS, the rules would be similar, but no. So there are safety concerns, and there's always going to be concerns with what you're flying, and NanoRacks will make that as painless as possible within the realities of the fact that they're flying on very large explosive devices. And so you do have to meet safety requirements for both. General issues, things are going to go wrong. Whatever you thought you were planning, it's great to have thoughts, it's great to have plans. What actually happens, you'll find out after the experiment's over. One of the first high altitude flights that I did, my partner's daughter was going through a science fair experiment, going to do a science fair experiment, and he asked me if I could build a very small data acquisition system. And you see my big ones. This one had to fit inside a ping pong ball to do a balloon flight. That was small. The first thing that I had him teach her was what Murphy's Law meant. Because something was going to go wrong. We didn't know what it was going to be. We just knew the odds were really high that in the process something bad was going to happen. And we finally got to a decision point where she had to make the call because I wasn't willing to. It was a small data acquisition thing. It was going to fly in a balloon in 2 weeks. We put a battery inside this ping pong ball that had 4 weeks worth of power. She had to decide whether it was safer to assume they were going to fly in the 2 weeks when they were supposed to, or if she wanted a switch that they might forget to hit. She chose the battery. It flew 5 weeks later. So you never know what's going to get you. All you know is sometimes you do reach decision points in your experiment where you're flipping a coin, and that can affect the outcome of what you're doing. Embracing the failure is a good thing, especially if there's a possibility of flying again. Because, what did we learn from that? Oh, maybe a switch was a safer bet. Maybe doubling up the battery would have been a safer bet. Maybe going out and helping them fly would have been a safer bet. There's no telling, but there were choices, and it was very specific decisions that had to be made that had a serious outcome on the experiment. In the case of something flying to ISS, every one of us has had a phone that stopped working, or a computer that just stopped working, crashed, did something that it wasn't supposed to. It's going to happen. The controllers that we build, and pretty much any controller and anything that flies, will have the single event upset that they like to talk about, sometimes worse. And what that means out in the real world is, okay, it's going to crash. On the phone, your choice is hold down the power button long enough for it to reset, pop the battery, do something. And not quite so easy on ISS. You're not real likely to convince an astronaut to go pop the case and fuss around. So generally on embedded things like this that have to come back to life like by themselves, you'll have a watchdog timer that if it doesn't sense any activity in the code within a certain amount of time, could be milliseconds, could be seconds, it'll punch the reset line, and more than 90% of the time that'll reboot it. However, see if we talk about that one. Yeah, we'll get back to that in a minute. Rebooting it is only part of the problem. If you've had the fun of having Word crash while you were halfway through a document that you forgot to save, yeah, you rebooted, your computer's fine now. You don't have your document anymore, but your computer's fine. If you know that you're going to have things like single event upsets and random reboots, and completely random, sometimes you may never get one. You might get one 5 times in a minute. You just won't know until you fly, because it'll be dependent on where you're flying and what's going on. If you know it's coming, you do things differently. You plan for it. You store the data often, but you also store checks with it and leave little trails in, whether it's on the virtual drive or in other parts of memory, leave trails so you can wake back up and say, okay, I was here, I didn't finish saving the last one, that last record is junk, let's move on, or I did finish it, everything's fine, let's just continue. It's just a few little programming tricks can be the difference between having valid data that can be reconstructed and losing lots of things. So as long as you know it's coming, it's not that big a deal. Experiments with liquids require double containment systems at least. NASA doesn't really like the idea of leaks, and especially water's one thing, but water is bad floating around randomly. So there will generally be a double containment at least. Though a lot of people use 3D printers to help build the insides of the little cubes, because they're cheap, they're easy, they're in a lot of schools, and you can do magical things, intricate internal 3D structures in your 3D printer. The catch is they're not watertight. But you might not know it for a few days. So you print one out, could make yourself a bowl, you print it out, put water in it, no water on the table, everything's fine. Leave water in it for 3 days, you look underneath it, you might have a bit of a puddle. So even things that would seem like they would be containment things and were easy to do, you have to sort of double check, and you do have to do some of the experiments on the ground over time, not just a quick, gee, here's liquid, didn't leak, we're good. Almost all over the table, which is why you need double containment. Then we have the issue of shipping. If you're building $1 billion satellite, you probably know where that satellite has been its entire life. You know where the parts came from. You know where it was constructed. You know the environment it lived in the whole time. You know the airplane that brought it, or barge, whatever, however you got it from where it was built out to the Cape. You know everything about that $1 billion satellite. It's documented, it's tagged, it's temperature controlled. You're likely to ship these things FedEx down to NanoRacks. It's not quite the same. So the bit where things are out of your control, well, that's a big place that's out of your control. You ship something to NanoRacks or down here in the middle of the summer, if FedEx is being sloppy, it could get quite warm. If you're doing a biology experiment, a life sciences experiment, it's something that you have to take into account, that maybe you need to ship your experiment on ice, dry ice, some kind of cooling thing, and possibly even have a sensor up your shipping container. Because if you're trying to grow some seeds that have already cooked to 250 degrees inside the shipper, they're probably not going to grow. And you might want to send back another copy of the experiment. If things get too cold in the winter, depending on where you're shipping from, it can affect life sciences experiments, or worse, it could crack something that's containing liquids. So the low cost of a NanoRacks experiment is actually a problem when it comes to knowing where your experiment has been, because on these budgets, you just won't know where it's been unless you carry it and keep it in your cooler and take precautions most people aren't willing to take. So again, it's not a huge issue. It's just on the long list of things to be aware of when preparing and designing your experiment, that you don't want to get caught by something that's completely avoidable. If everything else goes well, you launch. Well, that's a fun time for a piece of electronics, or especially a piece of biological gear. Yeah, you're rated at human. Well, most of the rockets aren't rated actually human anymore. That would only be the Soyuz. So you're flying unmanned rockets that you don't have a whole lot of guarantees about the shake, rattle, and roll, and the shaking forces can be pretty severe. So I don't know that NanoRacks puts things on a shaker table to do the test. Do you know if they do that one? If you have access to a shaker table, not the worst thing to use, within reason. You also don't want to destroy your experiment while you're testing to see if you built a good experiment. But you will have a lot of forces. One of the things that came up trying to do a plant growth experiment for a high school I've been helping down in Houston was they want water in a bag, and they want a valve taking the water to water the plants. And they pressurize the bag with a spring, I think. Well, that's all great, but during launch, depending on the orientation of the bag, which you won't know ahead of time, the forces on the bag can put an awful lot of force down on the valve, or if you're trying to use a pump, the force could exceed during launch whatever the pump is able to hold back, and so you could have leakage because of the launch forces. So there are the considerations taken into account about just the rough ride you're going to have for the 10 minutes to get on up there. And if you take into all of that stuff into account, well, we come back to what we can help with. We can help with the computer side. Our little computer it takes care of the USB for you. It's a general purpose. Let's see what's next. It's a general purpose computer. For people who know about small microcontrollers, it has an ARM Cortex M3 32-bit processor, cranking along at about up to 60 megahertz or so. People have been asking me about power consumption. Well, that depends. You can run it as slow as you want. You can put it to sleep, whatever you want to do with it. And the speed it runs determines the power draw. During a USB data dump, you're going to be drawing between 25 and 50 milliamps, whether you want to or not. A lot of the rest of it is sort of depends on what your experiment wants out of the board. full out, I believe the thing is running at around 100 milliamps, 125 milliamps. So it's a portion of the budget, but ideally it can do much of the work. Expansion connectors allow you to hook up pretty much any type of sensors you might want. It has analog to digital converters on board, digital to analog, a pile of digital bits, and expansion serial buses. And you can plug into the serial buses things like cameras, which a lot of people like, and make your own sensors or interface it to anything else that you may need it to do. We're adding on the rev of the board that you folks would have access to a version. We're adding some high power drivers to be able to directly control LEDs, like again for a plant growth experiment such as this one. You can see, assuming this is the pointer, up here they had 2 different color LEDs which they were cycling different times a day. So they were able to try to control the plant's version of daylight as the day went on. This is sort of a very much handmade add-on to one of the boards. Has some very high-power drivers to be able to run a solenoid, as well as a moisture sensor on that board to measure the moisture content of the soil that they were using. So it knew when it was time to water itself. So we made it as flexible as we could. We made it very programmable. The processor, which is up in that corner, is a Cypress PSOC 5. The beauty of that is you can download the entire developer's kit from Cypress free of charge, so everything it takes to program is, all the tools are free, and programming, debugging, and all that. We will be providing some sample codes to show how to do some of the things that it can do, so you don't have to start with a blank page. Also on board, if anybody needs it, we have a gyro there, 3-axis gyroscope, and it currently has 2 different accelerometers. One is a high G accelerometer, the other is a low G accelerometer. The low G is on station. The low G is really all you're likely to see data out of. If you see something while it's on orbit, if you actually see anything off the high G thing, that would be bad. The low G is about 0 to 2 Gs, so if you go above that on the station, something's going on you probably weren't expecting. It also has, I think, maybe the back, nope. On the back of the board, we have a micro SD socket to be able to put lots and lots of storage, and that's what's used then to pass off to the astronauts, which is then becomes your downlink. Let's see, we're working on a camera module for the people who need a camera. I think I found an off-the-shelf solution, and we're trying to work on one that perhaps will be a little bit cheaper. This camera, that's sitting on a dime, so it's essentially the camera out of a cell phone. The catch is you usually need additional optics to be able to focus within that 4-inch cube, because you have the board, then you have a camera, or you possibly have a daughter board, then you have the camera, and sooner or later you have to have your experiment that you're looking at. And so, it might need glasses to be able to see that close. Yep. The cameras that I've seen so far are running, I think the camera that's on my desk now is about 100 milliamps. The cameras are not free. The other problem with cameras is they're data hogs. I've had people say, I want to run 1080p, and I want to run it forever, and I want it downloaded. It's like, I can't do that with my phone. I can't do that with my camcorder. You have to choose what's important to you. Oh, if you're doing multiples, it's 100 milliamps when they're running. You don't have to turn the camera on. So most of the cameras have a power down mode where they're drawing more in the high microamps rather than the milliamps, so that drops down to the noise. Sorry, so the question was, would it make sense if you need an array of cameras to move the camera or to have an array of cameras? And I'm not a big fan of moving things if unnecessarily, because it's just something else to break. Whereas if you're turning the cameras on and off, a camera might break, but you still have the other, if you're doing an array of 9, you still have 8 left. But if you if you try to do an XY rack where you're moving stuff into jams, then it may be pointing at nothing. So from just a safety point of view, I'd take the more expensive route and just go with multiple cameras if that was going to be necessary. The other thing to be aware of, especially since Mike said you guys get to play with a 1.5U size, is the optics are, to get focus that close, you are likely to have optics which are likely to be slightly wide angle. So you may be catching your entire other end of the unit off of that one camera. You may not need multiple cameras unless you're trying to go for close-ups. Well, in which case, spin a holographic wheel. And there's any number of ways to get there. The simplest, most predictable way would be multiple cameras and just shut down what you're not using, because they are power hogs. But also, the plant growth people, sometimes they say, well, we want to take a picture every 3 seconds. It's like, why? Did you not go outside and watch the grass grow? That's a lot of data. If it's going to be even a decent size, if you burn the power to turn into a JPEG, and JPEGs aren't free, they cost you compression power. So if you burn the power to make them JPEGs, it's still at a couple $100K for a decent JPEG, and it adds up for a lot of frames that aren't anything interesting. What might be interesting is when it's time to water the plants, then you might want to try to run, if you could run at video rates, and that depends on the camera you find. I'm not going out of my way. I haven't found a video rate camera of this size yet. But if you could run multiple frames per second or a frame every couple of seconds while you're watering and water's floating around the chamber, that's interesting. That would be interesting to see, and maybe there's some valuable data there. But once that water has been absorbed, hit a wall, whatever it's going to do, you're waiting for the grass to grow again. And probably you don't need to see that every 5 seconds. It's the astronaut is floating by, is plugging in and dragging your data off, but if you've tried to copy MP3s over to your MP3 player, 10 gigabytes of data is still a lot of data to move, and it has to be downlinked, and if you don't need the data, if it's not worthwhile data, there's no really point in collecting it. But there are, would have a computer underneath making the decisions. If you just declared it's watering time, sure, turn the lights on, calibrate the lights, hit the water valve, you're really at that point powering up the whole chamber and watching. But once it settles down, cut the data rate back again. So anyway, there's what you can do with it really depends on what you can imagine you can do with it. It's, we're trying to provide a general purpose computer. Mike gave a huge long list of possible sensors and things you could do. How a pile of sensors and computers and all turns into the experiment, well, that's what we're all here to figure out today. And this is us. Got my email at the top here, if anybody needs to get hold of me. Our website doesn't say very much, but it is there. I'll get it updated one of these days. It says these things are coming soon, and well, I've been showing some that they're coming really soon. And if we can help, just contact us, and wish you the best of luck with your proposals. And any questions? Guess people asking questions left.
You can hear for a while, Steve.
Oh, yeah, I'll be around.
Okay, excellent. Thank you very much, Steve Bress. Thank you. That was excellent. Excellent. Thank you very much, Steve. And we're getting towards the end of our formal presentations for today, our workshop, but the private consultation, I see the UCF guys are heading over now. Good luck. And Todd. So just I want to thank everybody for being here today. I know the private consultations will be going on till almost 4 o'clock, so please avail of them and get as much information as you can. I want to thank everybody who's been here today. It's been a wonderful reception, and I hope you found it very informative. I hope you can put together some very interesting proposals and successful proposals. That would be fantastic. I certainly look forward to it. Just to thank our own team here for those who participated. So many names, I can't actually get into it all, but thank you again. For our live stream folks, thank you for being with us. I hope you have an opportunity later to go to the Space Florida website, look at YouTube, and you watch the highlights, maybe see yourself on YouTube, which is pretty cool. Right. Folks, thanks very much. It's been our pleasure. Really enjoyed it, and I hope you find it helpful and useful. And talk to those NanoRacks guys and get some great information. They want to help you, and we want to see you fly. How does that sound? Okay? Take care, folks. Thank you so much.